Welcome back to our course on mechanical behavior of materials part 2. So in the last lecture, we discussed about the initiation of fatigue crack, right? So we figured out that fatigue crack can initiate from intrusions or surface cracks, scratches, notches, or even from the interior defects. Okay, that is what we discussed. Today we will discuss about fatigue crack propagation mechanism. Okay, let's proceed. Fatigue crack propagation. Okay, so let me draw a schematic that is like a summary of what I'm going to discuss in this lecture. Okay, so this is your surface, and say this is under delta sigma. Okay, and crack growth direction is along this direction. Okay. Now the crack has initiated, say from intrusion. So this is my crack. Okay, say this is an intrusion. It might be notch also. So somewhere from the surface, because of the defects, the crack has initiated. Okay, now this crack is going to propagate. So its propagation is going to be first crystallographic, say something like this. Okay, then it will be more or less horizontal. And then again it will be horizontal, but I will tell you the difference here. Something like this. Okay. So we can have 3 stages of propagation. If you remember that I mentioned in the last lecture also, stage 1, stage 2, and stage 3. So till here, say we have stage 1. Then at this point, we have transition from stage 1 to stage 2. Okay. Now this here up to say this stage, we have stage 2. And finally, we have stage 3. And what you see here are voids, what we have already discussed when we are talking about, fracture mechanisms, ductile fracture mechanisms. Okay. So these are your voids and this forms in stage 3. And finally, you are going to have, say, fracture here. Okay. And crack growth direction I have mentioned here already, right? It is along this particular direction. So this is how once the crack has initiated, it is going to propagate. It enters in stage 1, then there is a transition from stage 1 to stage 2. Okay, and the crack path is almost perpendicular to the loading direction in stage 2. You can see here the blue one. Okay, so your loading direction is this. Okay, and the crack growth is almost perpendicular to the loading direction. As soon as the crack enters in stage 3, you have dominance of, say, uniaxial tension, and the mechanisms what we studied for void nucleation, growth, and propagation, as well as cleavage, they will be now active. Okay, that happens in stage 3, and finally your sample is going to fracture. So this is how fatigue crack propagates after its initiation. So now we'll go one by one, stage 1, stage 2, and stage 3. Okay. So first is stage 1. So if you see here, track path is crystallographic. You can see the purple one, right? It's not perpendicular to the loading direction. It is having some inclined angle as the track propagates. Okay. So why it is happening? So, you have a very small track length, right? It has just started propagating. So the track length is small. Okay. Now, if you remember, we are talking about fatigue, right? So delta K will be Y delta sigma root pi. Okay. So K is what? K is Y sigma root pi a. Since we are now talking about fatigue, K becomes delta K and sigma becomes delta sigma. We have discussed that, right? And delta K, it is K max minus K mean, and delta sigma is sigma max minus sigma mean. Okay, and Y is a structure factor and A is the crack length. Okay, so now we are having an applied stress of delta sigma. Okay, and suppose we are doing constant amplitude test. So delta sigma at first. Now this delta K is going to depend upon now A, right? As crack has started growing, A is small, right? That means delta K is also small. So driving force for crack propagation is also small, right? But it is propagating because that is sufficient. Although it is small, it is sufficient, but delta K value is low. Okay. So what happens? You are going to activate single slip system. Okay, depending upon the slip system which is favorably oriented with respect to the loading direction, that will be activated in each drain in stage 1. Okay, you can correlate this with your Smith factor. So the low CRSS value is going to activate first. That is why you can correlate. Okay, so in stage 1, your track length is small. This means delta K is small, right? See the above equation. And if this happens, you are going to have activation of single slip system. And which is going to be activated? The one which is favorable to the loading direction, right? Correlate with your Smith factor or CRSS. So which are favorable to loading direction. Okay. So now it initiated, it started propagating, and now it at single slip system is getting activated. The track now encounters another drain. So another slip system is going to be activated now because both drains are having different orientation with respect to the loading direction, right? So track path is not going to change as soon as the track encounters a drain boundary. So track path changes at each drain because orientation is different for each drain. Okay. And when this happens, what you are going to obtain is the crystallographic nature of the track path, right? So leading to crystallographic nature of track path. That means faceted surface. Okay, so you are going to have faceted surface. So let me now show you what is the overall sequence in stage 1. So if you have this surface, right, and say track has initiated. So let me draw the drains first. and these are your grains. So track has initiated first, okay, and then it propagates like this. That is what we have discussed. Okay, something like this. Okay, so in each grain, it is going to change the path because the orientation of each grain is different. So this is your initiation here. And track propagation. Okay, so this is what happens in stage one. So if I now write overall sequence, so say you have now grain again, same. Okay, so what is happening after track has initiated? Okay, now you are going to activate single slip system, say something like this. Okay, so along that particular slip systems, your track is now propagating and you are having delta sigma. Remember, this is always surface here, right? Okay. Now, as soon as it encounters the grain boundary, which is here, right, it is going to change the path. So it is going to go to another slip system. Now will get activated. Now it has encountered the third one, which is this grain boundary. Okay. So say another slip system will get activated, something like this. Okay. And this is how track propagates in stage one. Okay. So and so on. So this happens for only a few grains. And after that, there is a transition from stage one to stage two. We'll discuss why that happens. Okay. So now if you see the front surface of the track, it is going to look something like this. Another track. Okay. So this is your front surface. This is not the same track. So this is not the same one what I have drawn. Just a schematic showing another track, but you can see it's a having a faceted surface, right? So, but this is the front surface. So what you are seeing here is the activation of in the slip system. So these are your slip bands. And this is your fatigue track. Okay. So this is air here, right? This is a track you are seeing from the front surface. Okay. So this is how track propagates in stage one. Now, after some point of time, the track length has grown to some extent. Track length has increased. What does it mean? Your delta K has also increased, right? So now, instead of single slip system, you are going to have duplex or multi-slip systems being activated, right? Because now you have increased delta K in front of the track tail. So it will not be anymore the crystallographic nature. It is going to become planar. I will show you the schematic for better understanding. So now we are talking about stage two. So here track path is perpendicular or more or less perpendicular to the applied load. Okay. And why this is happening? So now you have increased track length. right? That means delta K has increased. Okay, remember what is delta K? Delta K is Y delta sigma root pi A. Again, sigma delta sigma is constant if we are doing a constant amplitude fatigue loading. So A has now increased, so delta K has increased. So this will lead to activation of, say, duplex slip. Okay, so more than one slip system is going to now get activated. Okay. And this, when this happens, you are going to get more or less track path which is perpendicular to the loading direction. Okay, so this leads to more or less track path which is perpendicular to the loading direction. Right? And in stage 2, we are going to form striations. We will discuss about this in the next lecture. Okay, so now let's draw an schematic for better understanding. So you have this surface from where track has initiated, and suppose these are your grains, right? So track say initiated here, then it grew along these directions. Okay, so this is stage 1. Now it is going to encounter stage 2 because track length has increased. So you are going to have activation of now multiple slip systems. Yeah, say here duplex slip systems. So this direction, in this direction also. Okay, and because of this, you are going to have track path perpendicular to, or say almost perpendicular to loading direction. Okay, so if I now draw the schematic again, what you are going to have these grains here. Okay, and then track path is going to be something like this. And then multiple slip systems are being activated. So this is how it grows in stage 2. Okay, so here this is stage 1, and then stage 2. And as usual, this is surface. Now, if you see the front view, so your track is like this. You're going to have slip systems being activated. Now your track is this one. Okay, so these are your slip systems or slip bands. And what you this see here, this is your fatigue track. Okay, so this is how now track propagates in stage 2. the track length has increased. So instead of single switch systems, you are going to have duplex or multi-switch systems being activated. Okay? And here you are going to form striations, which we are going to discuss in the next lecture. Now the situation is the track length has increased, significantly in stage 2. So your Kmax is now very, very high, and that is where we are now in stage 3. So here Kmax is high at this stage. And when this happens, mechanisms, whatever we have learned, during uni-HCl will work. Okay. And what are those mechanisms? So you are going to observe voids nucleation, growth, and coalescence, and or cleavage. Okay, so your Kmax is now very, very high. So whatever we have learned, you can directly apply there. Okay, it is predominantly now say uni-axial tension kind of thing, and void nucleation, growth, and coalescence will now become active. And that is why, if you remember the first point I mentioned here, right? So now you see all the voids here after stage 2. Okay, and in between you can also see cleavage, right? So this is your stage 3. Depending upon the material, it will show cleavage or void growth. Okay, or mixture. Here you have stage 2. And finally, it will lead to fracture of sample. Okay, so this is how fatigue track propagation occurs in different stages. It enters in stage 1, then goes to stage 2, and finally to stage 3, which leads to the fracture. Okay, so this is the mechanism of track propagation. We'll discuss about the striations formation in the next class. Okay, now we need to quantify. Okay, so it is growing. So how much it has grown after certain number of cycles, right? That quantification becomes very important, right? You would like to know when your sample or when your component is going to fracture after how many cycles, isn't it? So what you need to understand is dA by dN plot. Okay, so we need to quantify now the crack growth. The quantification of crack growth. Okay, so we are going to use the fracture mechanics concept, what we have discussed. Okay, so it started with Paris. It's not Paris, it's the name of a person, of a scientist, and you will know about Paris law in a bit now. Okay, and that was in 1960. And he proposed that fracture mechanics is a useful tool for characterizing crack growth by fatigue. Okay, so till now what we have discussed is SN plot, right? So we have stress in the number of cycle to failure, right? There we don't discuss about how crack has initiated and propagated. So we don't quantify about the crack propagation. What we know is how many cycles a sample is going to survive, okay, at a given stress or say load, right? What Paris mentioned that, we can use fracture mechanics concept and then we will be able to know how much a track has grown after certain amount of time or certain number of cycles. Okay. So since we are talking about fracture mechanics, we know track is already present. And then we are going to use the K, right? Stress intensity factor. And in fatigue, this is delta K, which is stress intensity factor range. Okay. So now let me draw dA by dN versus delta K plot. So dA by dN, and here you have delta K log scale. This is also in log scale. Okay. And then your plot is going to look something like this. So here up to say this point, you are in stage 1. Okay. Then up to this point where you see a straight line, this is stage 2. And here you have stage 3. And at this point, fracture. Okay, and this is what we typically in alloy systems. So we are plotting dA by dN versus delta K. Delta K, it is for stress intensity factor range. dA by dN is numerator is dA. So the increase in the track length and denominator is dN. So number of cycles for that particular increment in track length. So dA by dN is meter per cycle. That is the unit. Okay. So what we observe here is there are 3 distinct regions. Okay. At intermediate delta K, the curve is linear. Okay, so we are talking about now this particular line. So this is linear. This is at intermediate delta K, and here you are going to have Paris law equation to be valid. Okay, in stage 2. This particular point at the bottom, we call it delta K TH. Okay, and TH is your threshold. So delta KTH is your threshold stress intensity factor range. Okay. And how do we know what is the value of KTH? delta KTH. So it depends upon the value of dA by dN, right? So for all practical purpose, we assume that below delta KTH, the track growth is not occurring. Okay. And this particular value will correspond to about 10 to the power minus 9 to 10 to the power minus 10 meter per cycle. Okay. So delta KTH. So this is the threshold stress intensity factor range. So this will correspond to dA by dN value of 10 to the power minus 9, 10 to the power minus 10 meter per cycle. Okay. You know, in many books, you will see that it's written below delta KTS, there is no track growth, right? So it's not completely correct because track is growing, but the rate at which it is growing is very, very small. So for all practical purpose, we are assuming that it is not growing, right? See, the rate is 10 to the power minus 10 meter per cycle. Okay. So this is the meaning of delta KTH. Okay. So it's too low track growth rate that we assume that track is not growing. Okay. Now, if you see linear regime, so here we are going to have Paris law. Okay. So what is Paris law? So it can be given as dA by dN C delta K to the power M. Okay. And we are talking about log scale in the plot, right? So if I take log dA by dN, it becomes ln C plus M ln delta K, right? So now it becomes a straight line, and that is what you see happening in stage 2. So this is a straight line. M is your slope of straight line. Okay, and ln C is the intercept. Okay, so if you want to know M and C, you have to plot it and see whether what is the intercept and what is the slope. You will be able to know what is M. So typically for most metals, M ranges from 2 to 4. And we are talking about in air. We are not saying that it is in corrosive medium. In corrosive medium, M is going to be slightly higher. That means track rate is also going to be higher. Okay. So here you are going to have Paris law being activated in stage 2. So you can nicely use that particular equation. So I hope you have understood the concept of delta KTH. Now Paris law. Okay. And here the final fracture, wherever it occurs, right? This is your KC. Okay. Later on, many researchers actually mentioned that it not only depends upon delta K. So if you see Paris law, we are saying that dA by dN, the track growth rate depends upon delta K, right? But later on, it was found that it doesn't only depend upon delta K, it depends upon R ratio, also the history of loading, right? Loading history might change. So if it is not constant amplitude testing, it's a variable loading. So that will also affect your dA by dN, right? There is effect of underloading, overloading, etc. That we will not discuss in detail. That is not part of this course. But you need to realize that this is the first equation which was given for track growth rate in stage 2. Later on, many empirical relationships came by considering R ratio effect as well as loading effect, right? Or previous loading effect, loading history effect. Okay. So, you know, one of the empirical relationship I will give you. Other than Paris. So it says dA by dN equal to C delta K to the power M. So this is same as Paris, but now they have included the effect of R ratio. Okay, so here we are including effect of R ratio. Okay, there is another relationship later developed by NASA. So it was developed at NASA by Foreman. Okay, and it can be used for all the three regions. So Paris law, if you remember, it is valid for region 2, stage 2, right? So this one equation, which is dA by dN equal to C delta K to the power n. So this is what Paris law is. Then we have addition of some terms with respect to delta KTH and KC. Okay, where P and Q, C, M are materials constant. Okay, so this is another relationship. So there are lots of empirical relationships. Okay, but you know, in most of the cases, even in most of the books, you will see Paris law being given. Okay, so this is how we quantify fatigue track propagation. So basically, you need to plot dA by dN versus delta K, right? So to do that, what you need to figure out what is delta K, and you need to figure out what is dA by dN. Okay. Now dA by dN includes track growth measurement, right? So you have to know how do you measure track growth, right? So basically what I'm trying to convey that how do you plot dA by dN versus delta K? So to do that, you have to first measure delta K and then you have to measure dA by dN to plot it, right? So to measure the track growth or track length, right? So you have to measure dA by dN. So now you have to measure this dA, and dA is your track length difference. Right? So you can use different methods. So this first one is your telescopic method. So what is happening? You have the sample, okay, and then you have a telescope which is attached to a camera. Okay, and what you are doing, the track is growing, you are continuously capturing the image of the surface. Okay, and when you do that, you can actually measure the track length with respect to the number of cycles in a fatigue loading. Right? So that is method one. But here what you are going to get is the track measurement at the surface, right? And remember, we have already mentioned the track length changes, right? From the surface to the interior, the effect of plane stress and plane strain that was discussed before in one of the lectures, right? Now, second method is the clip gauge. You know, most of the people use it. So here you are using clip gauge, which is this. And I mentioned about clip gauge also when we are talking about fracture toughness measurement, right? So what you are measuring is the opening, but you can calibrate this opening with respect to the track length, okay? And based on the opening, you can measure track length. So now you are going to get the three-dimensional nature of the track length. So you are going to incorporate, you know, through the thickness track length here. So that is number two. So this is number two method, right? Now this third one is the potential drop measurement. Okay. So where you are going to measure the drop in the potential because of the increase in the crack length, because the material resistance is going to change, right? Because of the presence of the crack length. So you are going to measure the potential drop. Okay. So these are the typically three methods people use. There are other methods like X-ray tomography, where you can actually visualize in 3 dimensions how crack is propagating. Then you can measure, the crack length change with respect to number of cycles. Okay. So this is how you measure crack length. So now the first term here, dA by dN, you know how to measure it with respect to number of cycles. Okay. Now let's come to the measurement of delta K. Okay, so to do that, we have to use some samples, right? So we are going to use, when we do fatigue crack growth measurement for alloy system, we are going to use ASTM E647. I have mentioned here. Okay, so it's ASTM E647. Okay. So if you go through that, it talks about the standard method of crack growth rate measurement in metallic systems. If you want to do fatigue crack growth measurement, the first step is to generate pre-cracking. So this is what sample? This is compact tension. CT. So we are doing pin loading here, right? This one also I have discussed, and this is your notch. What I have shown here is the pre-crack. So if you see this line, right? This is your pre-cracking. So now you can see the difference between the notch and the crack. So crack typically is much sharper, right? It's very, very sharp, so that you can apply LEFM very nicely. Okay, so this is a compact tension specimen. So I have brought some of the samples. So you can see this is compact tension specimen. Okay, so you have this pin loading sample here. So you can actually put your pin. This is I'm using now pen. Okay, so you can put pin here and then you can apply load. Okay, and what you see here is your notch. Okay, so this is your notch, right? So this is one specimen. Another compact tension specimen. Okay, so you have these pins here and then you have this notch. Okay, so these are two large specimen. I have a smaller one. So this is the small compact tension specimen. Okay, so again you can see pin loading configuration, and then this is your notch. Okay, the sample I showed you with pre-cracking is this one, where I don't know whether you can see the pre-crack. Okay, but that image I have shown here in this particular slide. So you can see the low pin loading here. You have this notch, right? And here you have a pre-crack, okay, which I have shown here in the image. So these are the compact tension specimens. So I have brought another samples which I have already discussed before. So this is your hourglass sample, which you use for RR mole type test, right? So rotating bending test where R is equal to -1. So you can see it's a hourglass sample, isn't it? So what you have to do, you have to grip it like this, and then this will be under 4-point bending. We have discussed that, right? And then you can use this test. Okay, see the shape is hourglass. Okay. Now I have brought tensile specimens also. So different kinds. So this is the rounded tensile specimen, but this is threaded one, right? So there will be drapes where you need to fish this specimen. Okay. Another one, again rounded one, but here you have to, drip it. That the first one was a threaded one where you have to fix it, right? Here you have to drip it. So there will be 2 drips and then you can do tensile test. So this is another tensile specimen, but this is flat dot bone, right? So it's called dot bone sample. So you can again drip it and then do tensile testing. Okay. Another one where it is not the drip one, but it is pin loading. So you can have your pin loading here. Okay, these two, right? And then you can perform testings. I brought another one where you can see the notch. You see here, very small notch is there. Okay. See here, this is the notch, right? On both the sides. So this is the through thickness notch. Okay. So this is like single edge notch specimen where notch is present on a single side. What you see here is your impact testing specimen, the Sharpie one. Okay, so this is the specimen, and what you see here on the top is the notch. Okay, so you place your specimen and then hit it here on the opposite side of the notch. Okay, so this is your notch here. You can see notch, right? You can clearly see notch here. Another tensile specimen, but very, very large. Okay, large specimen, tensile specimen. Again, you have to drip it and then pull it. These are metallic system. You can do the same with polymers. These are your, this is your polymer sample. Okay, so polymer tensile samples. Okay, so I just wanted to show you some of the specimens configuration, right, in real picture. Till now, I had just drawn it on the slides, right? So for better understanding, I just wanted to show you. Anyway, so we are going to use, say, ASTM E647 for fatigue crack growth measurement. And first step is to do pre-cracking. Now, this ASTM standard contains about, the conditions of pre-cracking, how much you should pre-crack, what should be the load criteria, how much should be the crack increment between each decreasing in, delta K, etc. Okay. So if you want to do fatigue testing, you have to follow this ASTM E647. So there are 2 methods. One is decreasing K test. Okay. So where we actually decrease delta K. So we either keep R ratio constant or Kmax constant. Okay. And second is constant load amplitude. So if we keep the constant load, right, and in what will happen during fatigue, A is going to increase, so delta K is going to increase, right? So there are 2 methods. One is decreasing delta K, the top one, and the bottom one is increasing delta K, right? You can follow whatever you want to do. So what is happening if I want to do the test? So the first step I mentioned is the pre-cracking, right? So suppose I have this notch and then I did pre-cracking. Okay. Now I am doing fatigue test. So we have to measure dA by dN. And the second thing what we have to measure is delta K, right? So for delta K, you need to know A. Okay. So what is happening? Suppose I now did the test for certain number of cycles, say N1, and my crack length grew up to this particular point. Okay. So say N1. Then I again did, and then it goes to say N2 to some another length. And the crack length was initially say A1. Now it's A2 and then A3, right? So for N1, you can measure what is dA. So dA for N1 is going to be A2 minus A1, right? And then dA by dN, you can nicely calculate. It is going to be A2 minus A1 by N1. So I'm trying to tell you how do we actually measure dA by dN experimentally. Okay. Now, how do you measure delta K? So at point A, let's say this is point 1 and this is point 2 and this is point 3. Okay. So at point 1, you can have delta K 1 because you know what is the track length, you know delta P. So this is compact tension. So if you go through our previous lecture, you know the equation for delta K. You know F A by W. So you know what is the equation for delta K. That will be given in terms of delta P, A by W and track length. Right? So delta P is known because you are doing the test. So you know what is delta K1. Similarly, you know what is delta K2. Right? So to have the what is delta K, if you want to plot, you have to take the average of this. That is one of the methods you can nicely use. Okay. So if I want to plot, say dA by dN versus delta K. Okay. So for say n1 number of cycles, I got dA by dN. Okay. And delta K I also know is going to be somewhere here. So I got one particular point. Okay. Now similarly for N2, dA will be A3 minus A2. So dA by dN will be A3 minus A2 divided by N2. Okay. And delta K, right, between 2 and 3, it will be delta K2, right, plus delta K3 divided by 2. Okay. So you can have now delta K is going to be higher, right? So say somewhere here. So this way you can actually plot for each increment of the track length, what is the value of delta K average and corresponding dA by dN. So you can actually have different values of dA by dN versus delta K. Okay. And then you can plot the curve what I showed before. Okay. So let me show you the real data. So this is the actual data for fatigue track growth. Okay, so we know what is W, we know what is sigma, we know what is initial crack length, etc., etc. Okay, so what we are doing, we are having a constant R, 0.65. So I'm showing you how do you actually obtain that particular dA by dN plot. Okay, so we know what is P max. Suppose we fixed it. So since R ratio is fixed, P mean is going to be fixed. So that becomes 2136 in that particular case. We run for a certain number of cycles. Okay. So for delta A, so it was initial is here and final is here. Okay. So we know K max, K mean we can calculate initially and then we can calculate delta K. Okay. So suppose my track is growing from point 1 to point 2. So this becomes initial. This becomes final. Okay. And for initial, I already mentioned you have to delta K1 will be initial and delta K2. Okay. So this is how you do it. So after certain number of cycles, so here is your track length, final track length, what you are measuring. Okay. So you can measure what is delta A and you know what is number of cycle here. So you know what is dA by dN, which is being calculated here. Okay. So this is say dA by dN and this is your delta K average, the last column. Okay. What is delta K average? Is the delta K1 plus delta K2 by 2, right? So you have to take average of this value and this value. So you get this value. Okay. Similarly, if you take average of this 5.7, 5.42, you are going to get 5.56. Okay. So for each value of delta K, you know what is corresponding value of dA by dN, right? And what we are following is decreasing delta K method. Okay. So what we are doing is, so let me first draw the plot itself. Okay. So you are going to start at this particular point, somewhere in Paris region. Okay. And you are going to move downwards. And that is what is happening, right? So you started with 5.68 with a dA by dN of 10 to the power minus 8. Then it goes to 5.56 with a dA by dN of 7.70, 10 to the power minus 9. So you move down. Okay. And this is called decreasing delta K method. I discussed that, one of the methods, right? And to do that, if you see here, you are actually decreasing P. Okay. So you are moving downwards till you figure out what is delta KTH, which will correspond to about 10 to the power minus 10 cycles, right? Which is in this case here. Okay. So at 3.75 delta K, which is delta KTH, your track dA by dN is 1.73 10 to the power minus 10. Okay. So now you have figured out what is your delta KTH. Now what you do after delta KTH has been found, you need to know this part now, right? You have already obtained this particular curve based on what we just discussed, right? To do that, you follow constant load test. So this is constant load. Okay. And from here to here, you have decreasing delta K. So now load is constant, A is continuously increasing, so delta K is going to continuously increase. So what is happening? It is going to follow the same path, something like this. See the green color, right? And then you can obtain the rest of the part here also, and your sample is going to fail. Okay, and that is what is shown here. So your delta K, if you see, it is increasing here. Okay, and on the top from this point up to this, your delta K was decreasing, right? So your delta K is increasing, and you can see at the bottom your track length, track growth rate is also increasing, right? So you are going to follow the same path, and finally you can obtain the rest of the part which was not obtained before. Okay, so this is how we do fatigue track growth rate measurement experimentally. So you start with the Paris law regime, you do constant decreasing delta K method. Okay, so your delta K is decreasing, your track growth rate is also decreasing. And then you are going to obtain delta KTS corresponding to 10 to the power minus 10 meter per cycle track growth rate. And then you are going to follow constant amplitude loading experiment. Okay. That means you are going to increase the track length, and that means you are going to increase delta K. Right. So you again follow the same curve, and then you can determine the leftover part before, and then your sample is going to fit. Okay. So I'm going to stop now, and in the next lecture, we will discuss about the mechanisms of formation of striations, and I will also show you some of the vectographs and schematics. Okay, thank you.